Hi, welcome to Lecture 1 on torque and balance. Here I'm going to introduce the basic notion of torque and go through a number of examples. Torque can, broadly speaking, be characterized as a rotational push or pull. The analogous concept is of force in linear motion. Forces can try to cause accelerations. If they're not balanced out by other forces, they will cause accelerations along a line. Similarly, torque is attempting to cause a rotation, but there could be a situation where the torque gets balanced out by torques pointing in the opposite direction. So let's look at some examples in order to see what we mean by this concept. The first example I'm going to look at is you're trying to open a door. Now, here you can see a door. The view is from above, so you can see the hinge right here, and we're kind of looking down onto the door, like through the ceiling, I guess. Now, normally to open a door, you'd push somewhere near this end here, right? You'd apply a force here. And that will create a rotation around the hinge, where the hinge is our pivot point. Right? This is the point that stays fixed, around which the rotation occurs. So we call this the pivot, or the pivot point. Now normally you would be pushing here, and that makes opening a door easy. You could imagine instead that you push here, right? Maybe you can just, if you stand next to the hinge, you can try to just push against the door here. You can do that right now if you want. Just find a door near you. You push here, and you can tell right away it's a lot harder to open the door by pushing here as opposed to pushing here. So somehow the effect of your force on rotation depends on not only how strong is the force, but also where is it acting. Is it acting out here, or is it acting here? Now a game you can imagine perhaps playing is you try to push out here. Somebody else might be pushing with the same force in the other direction, but they're pushing in here. Well, you're going to win. Or conversely, if you imagine you're playing this game maybe with a small child, they might be pushing against the door here. You push the other way. It's a battle of strength. But to make it fair, you push close to the hinge. That's giving you a harder time. This is the concept of torque, right? Torque is created by forces. Let's say a force causes a torque, for example, pushing here with your hand, pushing there with your hand. But the torque itself, the effect on the rotation, depends not only on the strength of the force, but also where it acts. Let's look at another couple of examples where that becomes apparent. The second example is the one I picture right here. Imagine you're trying to lift up a fairly heavy, long rod. Now the way to do this would be, the easiest way to do this, would be just hold it roughly in the middle and you raise it up. Now you have to support, with the force you supply, you have to support the rod and essentially cancel out its weight. So if I were to draw the forces acting on the rod, then I might draw the mass here, the mass here causing the weight, of course, so the weight is down. And there'd be normal forces supplied by my hands. I guess maybe there are two small normal forces like this. Of course, strictly speaking, the weight is not just here, it's acting over here, and we'll study that in more detail in the near future. But let's compare this situation that is going to be fairly straightforward, very easy to do, compared to this situation here, where you're trying to lift up the same rod by the end. And that's going to be a lot more difficult to hold this rod vertically, to stop it from essentially falling down. Well, if I draw the forces here acting on this one, then there would be a weight that's going down here, and as I said, we're going to prove later that it is indeed okay to pretend that the weight acts right in the middle of a rod like this. Whereas the forces you're supplying, right, you're supplying them here. And the forces you need to supply here just by, you can try this right now, find a long piece of metal or plank of wood or whatever. It's a lot harder. You have to push a lot harder here than you would have there. Not only that, you also have to then somehow support it with your, maybe clamp it under your arm to stop it from just sort of falling down, right? From just falling down like this. So even though the rod has the same weight in both cases, it seems to matter hugely where I'm able to apply a force in order to keep it balanced. And in this case, I have to not only supply an upwards force here. If I just supply that, well, this side might go up, but this side will go down, a rotation, right? I also then have to, say, clamp it under my arm or hold it in place in some other way, maybe with my second hand further back, to stop any sort of motion like that. And we'll analyze that situation in detail later, but right now it's just our motivation to understand, look, there's something about torque that is different from forces, right? Forces just act in a certain direction on an object. We are now also concerned with where exactly on the object are those forces acting, because that has an effect on whether or not, or to what degree, that force is effectively trying to create a rotation in the object, right? In the case of the door, the rotation is obvious what it means, swinging like this. In the case of the rod held like this, the rotation would be well, we're trying to go down, right? This is we're trying to fall downwards. As you can tell just intuitively here, the rod is not going to try to rotate this way or this way, because the weight is right in the middle. Right, so the fact that the weight here acts not around the pivot point, which would be your hands, this would be the point around which the rod would be trying to fall, while here the weight's acting straight down in the middle, those two normal forces are left and right, it's not inducing any form of rotation. Of course, we'll make all of those concepts precise, but right now I hope you can see our motivation to introduce this concept of torque. So let's look at torque in more detail. Here's our key insight. Forces cause rotations, and they cause rotations based on where they are acting. We saw that, for example, with the door, or trying to hold up a long bar, where they're acting relative to a pivot point, the point around which the object might rotate. How strong they are, that's fairly obvious. If I push harder, I'm trying to induce more rotation, as it were. And also in which direction they act. And that's not only am I trying to open the door or close the door, we can envision some other scenarios. Let me come back to the door example for a second. So here is my door. I can imagine acting a force right here near the end, and that'll attempt to move the door this way. Now I could push the other way. Okay, then I'm trying to move the door the other way. Maybe it can swing freely, or maybe it would cancel out somebody else pushing this way. But there are other directions too in which I could act the same force at the same point. Suppose I somehow push the door this way. I was clamping it here and pushing this way. No matter how strong I push, this force is never going to cause any rotation in the door, because it simply doesn't push either this way or this way. It tries to, I guess, pull the door out of its hinge sideways. Right? So this force here creates no torque, even though it's acting at the same point and with the same strength as this force. Another force, say this one here, would be sort of somewhere in between. This one has a component that tries to pull the door out of its hinge sideways, right? But it also has a component that attempts to sort of push the door downwards. So if all those forces are the same strength, then this one here creates the most torque, this one here, and I know I'm pointing with arrows to arrows, but you know what I'm saying. This one creates no torque. Because it's neither trying to push the door clockwise or counterclockwise. And this one creates some torque, right? But it's not nearly as effective as creating torque as this one here. Creates some torque. So let us just to clarify this, make the following comparisons. Let's have 3 little doors, and on each one we're going to act 2 forces. So here's my first door. Suppose I just take this example right here. Let me make my force maybe red and blue this time. I've got one force acting like this, and I've got one force, same strength, acting like this. Which direction is the door going to start to move? So let me write this down. Which way will the door swing? In this case, if they're the same strength, the door is going to start swinging this way. Or it's going to go counterclockwise or anti-clockwise. Those are the same strength, but this one has the better angle. Let's try a second example. Suppose I have a situation where I've got the same door, and I've got 2 forces, and now they're acting in the same direction. One pushes here, one pushes here. Not same direction, same force, but along the same line, but in opposite direction. Which way is the door going to rotate? In this case, well, I think that's the first example we look at, so you know the answer. It's going to swing this way. This force wins, even though they're the same force, because this one here creates more torque. Now let's look at one more example. Let's say, and this one's going to be the easiest one by far, actually. Here's my door. Let's imagine I'm having that same force, but now it's opposed by a force that is at the same spot, at the same angle, like along the same line, but it's simply bigger. Which way is this door going to swing? Well, I think it's fairly obvious that this one's going to go this way. Clockwise. Right, so I might abbreviate this counterclockwise, counterclockwise, clockwise. Anti-clockwise, counterclockwise mean the same thing. I think counterclockwise is more the British term, anti-clockwise more the American term, but they're really entirely interchangeable. So can we quantify this? Well, let's define torque. Should we start a new page for that? Define torque mathematically. So torque is often given the symbol tau, like a lowercase tau. You might have met that in other contexts. It's just the Greek T sound, lowercase. I guess capital T was used for, maybe it's already used for tension all the time, or period. And lowercase t usually means time, so someone in the past decided that they're going to go Greek and go with the lowercase tau. The uppercase tau just looks like a capital T, so that'd be useless to use as well, because we couldn't distinguish it from a normal T. So tau it is. And I'm going to write down what the expression is. It is the radius from the pivot times the strength of the force times the cosine of the angle. I'm going to show you which angle I mean. Let me draw a picture here. So here's my door, and let's suppose my force goes this way, my force F. Then R is just the length, where is the force acting relative to the pivot point, and theta would be this angle here between the tangent, right? Imagine this point here would be sort of swinging in a big circle. Well, the tangent line, that would be the best direction to act the force if you want to create a big torque. So F cosine theta, this together, is essentially just the component of the force in the direction of the tangent. So that is what counts. The so-called radial component, whether the force is pulling in or pushing out, has no effect on creating torque, right? We saw that in the example right here, where we said this one here creates no torque. This one has a radial component that's pulling it out, that creates no torque, but it also has a tangential component, tangential to this circle, this arc along which this point here would move if the door were to swing. I can also write this in a different form. I could also, if I wanted to write this as R dot F, R times F times the sine of an angle. If I call this angle phi, then phi would literally be just the other angle here. Let me add it. And that's because the cosine of this angle is the same as the sine of this angle, of course. Right? The cosine of 30 is the same as the sine of 60. The cosine of 80 is the same as the sine of 10, and so on. So those are two ways to write an actual expression for torque. So now let's apply this to some example to actually do some calculations. Here's the example I want to look at. I'm imagining a seesaw, maybe on some kind of playground, and there's a child of mass 30 kilogram sitting on one end. Right now this child has no friend. What is the torque created by that child? Now, of course, we look at this and we immediately see the seesaw is gonna do this, right? It's gonna go down. So what is the torque that's created by the child sitting there? Well, let's draw the force on the seesaw. Now, we might say it's the weight of the child. That's not quite true. The weight of the child acts on the child, and then there's a normal force from the seesaw on the child. But because of Newton's third law, that same force is acting downwards on the seesaw, right? So let's say this again. The weight acts on the child, but we care about forces on that wooden beam. But because the child is supported from the beam, there's a normal force up, and the normal force goes both ways, Newton's third law. So there's a normal force acting on the seesaw right here. But for all practical purposes right now, it's a bit of an approximation. If this thing was actually to move, I'm going to say that the weight of the child essentially acts here. But strictly speaking, it's normal force. So what is the weight of the child? Well, it's mg, of course. So let's calculate the torque. Maybe the child is standing on the ground, to stop the seesaw. Or maybe somehow the seesaw is held in place with some other force. We're just interested in calculating the torque created by the child sitting on the seesaw. And the child is sitting 2 meters from the pivot point. So the force is straight down, right? So theta is going to be 0. So the force is mg, which is 30 kilograms times 10 meter per second squared. I know it's 9.8, but that's just going to make kilograms. make everything more complicated in terms of looking at the numbers. So we're just going to pretend we live on a planet where the acceleration due to gravity is 10. It's close enough. Right, we're lucky in that sense that we do live on a planet where we can make an approximation. If we lived on Mars, where it's something like 3.7 meters per second squared, we'd have a hard time rounding that to anything. But 9.8, let's say it's 10. So what does that make? That makes 300 newtons. So 300 newtons, they're acting here. The angle is 0 degrees, or we could speak in terms of the other angle phi, which would be 90 degrees. Of course, we can also express this in radians. Right now, I'm not going to do this. In the future, we'll probably use primarily radians, actually, but we'll come to it later. And then the distance from the pivot point at the radius of rotation, that would be 2 meters. So that makes the torque 2 meters times 300 newtons times cosine of 0, that's just 1. So that makes 600. Now what are the units? We haven't talked about that yet. Well, meter newtons, more commonly called Newton meters. So this is our unit of torque. Newton meters, force times a distance. The distance being the distance from the pivot point. So this is our first example. Now let's modify this example ever so slightly by making our seesaw not horizontal. Seesaw, now it is not horizontal. So maybe the child pushed off and now it's up in the air. It's about to come back down. Well, let's have a look. Imagine looking something like this, with the child sitting up here, holding on, having fun. Got hair now too. Alright. So the difference is that now the seesaw is at an angle. Let's make the angle from the horizontal, let's make that 20 degrees. Why not? 20 degrees. So the weight, right, the weight is still acting downwards, and according to the normal force between them is still vertical. So this is still mg. However, what's changed is that the tangent to the circle of rotation is this. Right? The most effective torque, or a force that would be most effective at creating torque, would be pointing in this direction, always perpendicular to the radius vector, that displacement of the point of action of the force from the pivot point. So that the weight isn't acting along that line. In fact, it's easy to see that this here is also going to be 20 degrees, right? Because this whole thing has just shifted by 20 degrees. So here they were exactly along the right direction, tangential to the line connecting the pivot point to the point of action of the force. Like this line here is perpendicular to the line in which the force acts. Well, now that's no longer quite true. Now there's an angle between them. So we can do our calculation. The torque is going to be the distance times the force. Now those haven't changed, right? It's still 2 meters from here to here. Still 2 meters. The child hasn't changed his or her weight either. Cosine 20 degrees. Alright, so it was cosine 0 before, now it's cosine 20, and the cosine of 20 is something like 0.94. It's not huge. I mean, you can tell, right? Most of this force is still acting in the right direction to create torque, but it does have a small sort of radial component. So if I split it into components, radial and horizontal, it would look like this and like this. And this is the component we want. It's not quite the same as the force itself, but it's fairly close. It's only 20 degrees off. So the cosine of 20 degrees, 0.94. So we plug in those numbers, 2 meters times 600 newtons, remember that was the weight, or the normal force between them, times 0.94. That makes, what am I doing? Excuse me, the force was 300, 600 we got by multiplying by 2, right? 30 kilograms times 10. I'm going crazy here. Okay, so 600 times 0.94 comes to, I think, 564 Newton meters. So less torque than before. Before it was 600. Now, if you had another child on the other side and they were swinging back and forth, I mean, would that change? Would the change torque change whether or not they're balancing out? It wouldn't, because if there was another child here too, that child would also be at an angle of 20 degrees. And their weight would also have the same factor come in when you calculate the torque. See if you can make sense of its statement by drawing it out yourself. Alright, so we've calculated a couple of examples. Now, what do torques actually do? Yes, they cause rotations, but can we be more precise than that? Yes, we can be. So if a torque is unopposed, there's only one torque, or not completely, or only partially cancelled out, then it'll create angular acceleration. Right, angular acceleration. So the analogy is forces, right? Forces, just acting on an object, they can create an acceleration. What you would do is you calculate the net force. You might have an object that's getting pushed one way with 5 newtons, the other way with 2 newtons. Well, you can figure out what the acceleration is. Let's do an example. Let's compare this. Forces. Imagine I've got maybe a block here and someone's pushing it with 5 newtons this way. Somebody else is pushing it with 2 newtons this way. I know I haven't quite drawn those arrows to scale. That's okay. Say the mass is 6 kilograms. What is the acceleration? Well, I could find the net force, F net, is 5 newtons minus 2 newtons, which is 3 newtons. And then I can find A, the acceleration, that would be F net over M, 3 newtons over 6 kilograms, that makes 0.5 meters per second squared. Torque works exactly the same way, except we're not thinking about motion along a line forwards or backwards, we're thinking about rotational motion. So we similarly calculate a net torque, where we say counterclockwise torque minus clockwise torque, what's left over, and then that will determine the angular acceleration according to a law that is sometimes called Newton's second law for rotations. And we'll come back to that very shortly. Right now, we're just going to focus on static problems. What I mean by that Well, with forces, right, we had that if F net is 0, the forces balance out, then A is 0. So it could be that the object is at rest and stays at rest, or it could be that it is moving at some velocity while it will maintain that velocity. Say you're pushing a cardboard box along the floor, well, it has friction. If you push it with a force that exactly cancels out the kinetic friction, you'll be pushing it at a constant velocity. Same thing here. We'll look at this kind of situation, but for torque. So let's write this down. Similarly, there is a net torque and a Newton's second law for rotations, and we'll come back to those, I promise. Write it down. We'll get back to that. Right now we're going to focus on static situations. Cases where the net torque is 0. The net torque, I'm going to write it like this, equals 0. So-called mechanical equilibrium. In the past, you met mechanical equilibrium in the context of forces cancelling each other out. Right? The box being pushed along a floor at a constant velocity is mechanical equilibrium. Something hanging from a cable without moving is mechanical equilibrium. In that case, we'd say static equilibrium if it's not moving at all. So we're going to look at some cases where the net torque is 0, and we'll do some examples with that. So let me draw up an example for you. Here's the example I want to analyze right now. I drew it out for you. So I imagine there's some kind of log, a large, piece of wood. It's pretty heavy, and it's resting on one side here on some kind of rock. And on the other side, there's a poor parent holding it up, and there's a kid dancing on it. Now, we can't ignore the mass of the piece of wood itself. It's fairly heavy, heavier than the kid, in fact. I'm going to say the mass of this tree, as I call it, is 120 kilograms. The mass of the kid is 40. This thing is 2 meters long from there to there, and the kid is dancing right here. I'm about half a meter away from the parent. I'm going to pretend all those forces are acting right at a single point, right? I don't really care that there are two hands here. I'm just going to treat this as a single point. This is a single point, and that the log is resting on the rock right at the end. So what force does this poor parent have to provide to hold up this heavy log? That's what I'm trying to calculate now. So let's analyze what forces are acting on the log, right? The thing that might rotate. So one thing that the log has, it has its own mass and therefore its own weight. With an object that's extended, right? It's not a point. The log is not a point particle, clearly. It can't be, otherwise it couldn't rotate, it couldn't experience torque. It's an extended object. We can always pretend that all the mass is at the center, the so-called center of mass. I want to prove that to you right after this example. But right now we're just going to go with it. The weight of this log is acting in the middle. So the weight of the tree is acting right here. It's acting down, of course. The next force we have is the weight of the kid. And the weight of the kid is standing right here. So it's acting down. Now I'm drawing over my other length measurement here, but that's okay. It's smaller than this one, right? It's only 40 kilograms. So I know this is going to be less. So weight of kid. And again, I'm being a little bit careless here. Strictly speaking, it is the normal force between the kid's foot and the tree that's pushing down. Right? It's the normal interaction, not the weight itself. The weight itself is strictly speaking acting on the kid, but the kid is supported by a normal force from the log on the kid and by Newton's third law, that therefore is a normal force down, but I don't care right now. For practical purposes, it's the same as the weight of the kid acting down. So right now, if it were just those two, of course, the whole log would just tip down like this, because there's a clockwise torque that's not cancelled out. But our goal is to have it cancelled out, so in comes the very put up on parent that has to supply a force upwards, right? Normal force, let's call this F parent. Now one thing that's nice about this problem that makes it easier is that all the forces are acting vertically in a situation where the radial line, like the line between the pivot point in each of those points, is essentially horizontal. So the angle in all cases, that the theta angle, is going to be 0 every time. Right, so that's the first thing we're going to note. The angles are nice. Let's calculate the torque due to each one. So the torque due to the tree, that's going to be the weight of the tree, so the mass of the tree times g, that's the force, times that distance, which is, let's call it r3. By this I mean that the separation of where the force acts, and we can pretend it's all acting in the center for reasons I'm going to show you in a second. And then, of course, the r3 itself would be distance from here to here. So it'd be 1 meter. Let's do the math. 120 kilograms times 10 meters per second squared times 1 meter. That comes to 1200 Newton meters. Now, if you've been paying attention, you notice that the Newton meter is a kilogram meter squared per second squared, which is the same unit as energy. Right? So a Newton meter is also a joule. But notice that here that would be very confusing. In the energy, you've got a force acting in the same direction as a displacement to get work. That's how Newton meters comes about there. And it's not the case here. So we're not going to call this joule. We're going to call this Newton meters. Even though technically speaking, the units are mathematically the same. Alright, let's keep going with our calculation though. So this is the torque due to the tree, now to the torque due to the kid. It's going to be the mass of the kid times g times the distance of the kid from the point of rotation. So what's that? It's 40 kilograms times 10, because we assume this is on Earth, times, so the distance between this point and this point, it's not 1, it's not 0.5 either, 0.5 is going the wrong way, and if the whole thing is 2, and the kid is 0.5 from the parent, then this is 1.5 meters. So what does this come to? 400 times 1.5 is 600 Newton meters. So let's figure out, so those are the forces that act that are clockwise, so why not just make a little note of it here? I'm just going to put a little arrow in front of each one that shows the direction. So in a sense, torque is a vector. How to actually express it in vector form, like in proper mathematical vector form, is something we're going to come to a little bit later. We'll have to think 3D for that, but we'll come to that. But right now, we're just interested in figuring out, well, what is that force? Let's find the torque of the parent is clearly going the other way, right? Because the parent's pushing it up. If it were just the parent, the thing would start rotating this way. The torque due to the parent holding it up is, well, it's not a weight or anything, right? It's just the unknown force, the thing you want to find, F parent times the separation of where the parent is acting from the pivot point, which is 2 meters. So it's the unknown F parent times 2 meters. And that better be equal to what? Well, it better be equal to the sum of those two, because it'll cancel out those two. Right? So if I add those two, I'm gonna get 1800 Newton meters total. This is a total in the clockwise direction. We write it like this, like an arrow, sort of clockwise rotation, right? See what I'm trying to do there? 1800. So that better be equal to 1800 Newton meters in order to cancel out the torque going clockwise. This is the only torque that's helping the counterclockwise, right? It's stopping the clockwise rotation. So it's the only one. It has to be equal to 800. So we can see that the parent has to supply a force that's equal to 900 newtons. I'm going to squeeze this down here because it's simple enough that you can see it. F parent. I know you can't read it, but you know what I'm writing. 900 Newton meters. Right, this is my final answer. What times 2 is 1800? Well, 900 newtons. Alright, so that was a good little example. Now, the one thing I have left that I want to do is I want to prove to you, or argue first, sort of informally, then prove to you that it is indeed justified to pretend that all the weight of this tree is acting in the middle. So let's do that. So, why we can pretend all mass is at the center of mass when calculating torque. Let me give you the kind of intuitive argument, and then we're going to make it more formal. So imagine I've got a long piece of wood, like the tree we just talked about in the parent kit tree problem. Now, one way I may sort of visualize how the mass is spread out is that I cut up this tree, at least in my mind, into smaller chunks. Now, strictly speaking, you want to cut it like into an infinite number of infinitely small chunks, to be really precise about it. That's ultimately what we'll do. But right now, let's just chop it into 5 chunks. Just so we see the principle of what's going on. If this is 50 kilograms, say, then each chunk would be 10 kilograms. Now, this one here, right? This one here has a single force that be acting down. Find the torque due to that around the end point here. This is where the tree is fixed. So I can essentially replace this, or so is my claim, by a bunch of little weights acting like this. Do those two situations have the same torque? Right, here I'm pretending all 50 kilograms is right in the middle. Here I am pretending I have 5 small chunks. Well, let's do the math. Here, torque is gonna be 50 kilograms times 10 meters per second squared, like G, right? Times 0.5 meters, which comes to 50, 500, 250 Newton meters. Mathematically, I might say if this is length L, this mass M, right? Mathematically, algebraically in general, I'd say it's M times G times L over 2. I'm assuming, of course, that the rod is not, or this tree is not heavier on one side than the other. It's like a uniform distributed mass. The example, the method will work more generally if it's not true, but we're going to try to keep things simple right now. So what's the torque here? Well, the torque here, it's really it's 5 torques, right? It's 10 kilograms times 10 meters per second squared times how far is this one, this point here from here? Well, each segment is 20 centimeters long because this is 1 meter, right? So 20 centimeters, 20 centimeters, 20 centimeters. This is right in the middle, so this is 10 centimeters from here to here. Times 0.1 meters. Add to that, we're going to do the second one. 10 kilograms times 10 meters per second squared times 0. What? Well, it's going to be 20 centimeters to here, but we want to go to the middle, so another 10, 30 centimeters, 0.3 meters. Then it's 10 kilograms times 10 meters per second squared times, so this is right in the middle, 0.5 meters. Then 10 kilograms, now we're into the fourth block, times 10 meters per second squared times, okay, 20, 40, 60, plus to the middle 70, 0.7 meters. The last one is going to be 0.9 meters from the pivot point. 10 meters per second times 0.9. Now, of course, I can factorize that quite nicely. I'm going to get 100 kilogram meter per second squared. We add up those numbers. What do we get? We get 2.5 meters. And that comes, of course, to 250 Newton meters, which is reassuring, which is the same thing we found here. Now, if you think of this, if you leave L general, then this would be just 1/10 L, 3/10 L, 5/10 L. So I would write it like M over 5, the total mass, right, divided by 5, because I split into 5 chunks, times G, that's the weight of each one, times, now I'm going to add them, right, for each one. This is the same, so I can factorize it. I'm going to get L over 10 plus 3L over 10, so that's 1, 2, 3 half lengths, plus 5L over 10 plus 7L over 10 plus 9L over 10. And you can check, you add those up, you're going to get 25L over 10 divided by 5. You're going to end up with mg times L over 2 when all is said and simplified. So that's kind of our justification, right? It works. We split it into 5, it gives us the same. We could have split it into any other number, of course. It would have worked just as well. But into 2, into 10, into 100, into 1,000,000, into 1,000. Million, trillion. So you get the point, right? Okay, let's make this more formal though. Let's split it into an infinite number. How do we do that? Well, let's draw it. Let's make this our formal proof. And I'm only going to prove it for a long line of mass, like a long rod or tree trunk. We could extend this proof to work in more than one dimension, like if we put a giant sort of funny shaped board. You can still pretend all the mass is at the center of mass. But I'm just going to keep things simple and only prove it for a single long piece of wood. So here's my pivot point. And I'm going to say this whole thing has a mass m and a length L. So what am I going to do? I'm going to split this thing up into tiny little chunks. Right? And let me introduce a coordinate system. I'm going to say this point, this is my 0 point, and then this is my, let's call it R. This is 0. So I'm sort of counting, I can measure where is this, oh it's right here, at the value R. I'm going to pretend this has a width, and I call it dr. It's a little change in R as I go from here to here. Right, literally just mean the width of this. And I want to mathematically make this become infinitesimally small. Of course, I can't draw it infinitesimally small. So this is our chunk. What is the torque due to the one chunk? Torque due to one tiny chunk of width dr. Right, dr, one thing, is what I label the width. Well, that's going to be equal to the weight of this thing, so weight of chunk, times its position, its separation, its distance from 0. It's not L, right? L is the end point. This one is not L from the pivot point. This one is whatever that distance is. Let's call it R, because it's the name for the variable that denotes its position relative to the pivot point, times R. So what is the weight? Well, it's the mass of the chunk times G. Mass of chunk times G times R. The mass of the chunk is, well, I don't know, but I can figure out what fraction of the total is it. And if this is 1/100th of L, and if L is 1 meter, this is 1 centimeter, well then its mass, the mass of this tiny chunk, would be 1/100th of the total. If this width was 1/500th of the total length, then the mass would be 1/500th of m. So that's given by dr over L. That's the fraction of the bar that's taken up by the chunk times m. So I would get the 1/500th times m, if this is 1/500th of the total length, times G times R. Now we just have to sum those torques. Sum torques of all tiny chunks. What is that? Well, so the total torque is going to be equal to the sum of all dr over L times m times G times R from R equals 0 to R equals, well, where does the bar stop? At R equals L. Right? Now, if I have a finite number, if I have 500 of them, I could literally do this. It would take me a while. Maybe I write a piece of computer code that does it for me. I could literally do this. But we can do this analytically. Making those tiny chunks become infinitesimally small means the sum is just written as like this. This is literally a big S. That's where this symbol comes from. The integral symbol is a big S for sum. dr over L m G R from R equals 0 to R equals L. Alright, I'm going to write it like this. That's how we write the limits of taking the sum. Where does the sum start? Where does the sum end? That's what an integral literally means, right? It's an infinite sum of infinitesimally tiny chunks, which I start and end somewhere that I have to express in my variables. So I can do this because most of this is a very easy integral, right? It's going to be it is, what am I doing? It is going to be mg over L. Those are constants. They go out the front. Then the integral is r equals 0 to r equals L of r dr. That is easy. Mg over L r squared over 2 between 0 and L. When I plug in 0, I get nothing, so I just plug in L. So I'm going to get mg over L times L squared over 2. That's what I get when plugging in L here, which simplifies to mg L over 2, which is exactly the thing I wanted, right? It's the weight pretending it acts halfway from the pivot point. So this was our proof. Sometimes people finish their proof writing QED, quod erat demonstrandum, what was to be proved, right? It's Latin. Alright, so that proves the assumption we've been making all along. Using an integral, and hopefully by now you've had some experience using integrals and understand what they mean, and again you're gonna get somewhat better at it in this course of really understanding, you know, what are they, how do I use them effectively. They're not these abstract, funny math things. Alright, and this is kind of where I want to finish this lecture. It's almost an hour long. That's a lot for you to watch. In the next lecture, we're going to do some examples, and some examples will include things like a drawbridge, a castle. What's the torque? What's the tension in those chains that hold up the drawbridge? At what angle is it highest, maybe? We'll look at a leaning ladder. Does it slide? Have a ladder. It's leaning against a wall like this. Right? Will it slide? Like, what does it depend on? And another couple of examples. Alright, I will see you in class or in the next lecture. Good luck with your studies.